So basically, for all of these cosmic questions, we have three approaches. Gravity is what's pulling me in a circle. I can only say that when I see the magic word orbit. I have work equals change in potential plus change in kinetic. I only use that if they ask me how much work. Otherwise, it's probably a change in height, change in speed, yucky curvy graph conservation of energy. G. So, number one, we're in orbit. I can start out by saying gravity is what's pulling me in a circle. On your test, I think I've said to you there are four ideas, concepts: orbital speed, orbital radius, altitude, and period. I'm going to give you one of them and ask you to find two of the others. I don't know which ones yet, but I'll probably mix and match in various versions. Here, I can say big G, big M, little m over r squared equals, since they're talking about speed, I'm going to go mv squared over r. M cancels. One of the r's cancels. How do I get rid of a v square root? They gave me this as an orbital radius. It's measured from the center of the planet, so I don't need to add the radius of the Earth to it. When I did that very, very carefully, did you all get 702 meters per second? Which is low, but then I went, wait a minute. The radius of the Earth is 10 to the 6th. In fact, if I go 8.1 times 10 to the 8th minus the radius of the Earth, and then divide by 1,000, this satellite is a ways out there. It's several 100,000 kilometers up there. So it doesn't need to be going very fast because it's not affected much by Earth's gravity, although we would have had to use a whole bunch of potential energy to get it out there. What's the kinetic energy? Well, now I just went straight a half mv squared. I got 6.16 times 10 to the 8th joules. There's two ways you could have done that. You could have used your v from part A, but I also said, oh, v squared is actually big G big M over R. This is that little trick that we learned last day as a handy little in your back pocket error check. The kinetic energy in orbit will be half the potential energy be in orbit, but positive. If you happen to have that potential energy kicking around, you could have just divided by 2, get rid of the negative, and you're done. Number 2, orbits. Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m4 pi squared r over t squared. How did I know to go with that? Because they gave me the period, so I'll use that version of acceleration. James, a little m still cancels. Does an r cancel? No. Common mistake, kids move this r to there, and they think, yeah, no, you've got 1 over r cubed, and we can't solve stuff that's on the bottom. So I'm going to move both of those r's to there. I'm going to move the t squared to here, and I'm going to move the 4 pi squared to the bottom. And that's going to give me r cubed equals big G, big M, t squared all over 4 pi squared. Evan, how to get rid of a cubed? You mean I get to use the cube root button? Oh boy, it's always nice when I get to use the cube root button. And when I carefully crunched the numbers, I got 1.80 times 10 to the 7th meters. Alex, what is meant by relative to 0 at infinity? What do we mean by that? That's me saying, please don't go MGH. The cosmic potential energy equation, that weird-looking one, we defined it as relative to 0 at infinity. So that's a trigger phrase saying, look, you better make darn sure you use negative big G, big M, little m over R. By the way, based on this, where would the potential energy be 0? All the way out at Infinity. That's why we say relative to zero at infinity. MGH, where is potential energy zero? On the ground. Okay. So you're going to use your R value right from there. And otherwise, it was careful plug and chug. I got negative 2.66 times 10 to the 10th joules. If you got that 3 out of 3. Mr. Dewick, how can we have negative potential energy? Here's what it's saying. If I wanted to get this out to infinity, where there's no potential energy, I would have to add that much rocket fuel. I would have to burn 2.66 times 10 to the 10th joules of rocket fuel to get to zero, to get all the way out to infinity. Number 3. So 1A and 2A were orbit gravities that's pulled me in a circle. 3 is asking me to find what, James? So change in potential plus change in kinetic. Do you see the word orbit? In fact, it says lifted. What we're trying to suggest is we're starting at rest and ending at rest. We've just lifted it up and then we're going to let it go. It's not in a stable orbit. What's change in anything? We get your, yeah. You got a little brother here, which is good too. It's strange how that's such a tough thing to say, but it is. So negative big G, big M, little m over. And I said to myself, you know what? Our final is going to be the altitude plus the radius of the Earth minus negative big G, big M, little m over radius of the Earth. Then I carefully started substituting in numbers. And I ended up with, on my calculator, that I was having fun and just pasting it directly in from the calculator. Did you get 2.71 times 10 to the 10th? Joules. If you got that, I would give you 4 out of 4. Otherwise, here's how I gave up the part marks. Can you give yourself a lovely score, please, out of 13? Lesson 5. Thomas, can you read me the title, please? Black holes are attractive, Mr. That's so fun. Okay. The second half of this lesson is going to be about black holes. But again, I want to show you some of the questions you might see in your future. Hint, hint. Suppose a 45,000 kilogram asteroid is traveling at 5.67 times 10 to the 4th meters per second at a distance of 1.2 times 10 to the 7th meters from the center of the Earth. How much kinetic energy would it have if it impacted the Earth? Huh. Kiefer, what's this question asking me to find? Are we in a stable orbit? How do you know? I don't see the word orbit, and objects in stable orbits tend not to crash into planets. Okay, so there's kind of a Captain Obvious there. So can I write gravity is what's pulling me in a circle? No. Did this ask how much work? No. So how am I going to solve this? Conservation of energy. I'm not going to go K equals a half mv squared because that would be how much kinetic energy it had in space. I want how much Ke it's going to have if it impacts the Earth. Newsflash, I think it's going to have more. So this is going to be Ke initial plus Pe initial equals Ke final plus Pe final. I really have trouble as a lefty making a capital E. That's an awkward motion. They just get worse over the years. Are any of these zeros? Well, Ke would be if we were stopped. Are we stopped initially? By the way, also please notice initial is going to be in space. Final is going to be on the surface of the Earth in this particular question. Are we ever stopped? Is our initial kinetic energy 0? No. What about our final kinetic energy? After we hit the Earth, it will be 0, but at impact, it's going to have a lot of kinetic energy. It's going to be moving. What about potential energies? Alex, where would those be 0? Relative to what? Infinity. Are we out at infinity here anywhere? What are we trying to find, Kiefer? Get this by itself, minus the PE final over. So I'll end up with this. KE final equals KE initial plus PE initial minus PE final. As an equation, it'll be a half little m V initial squared plus negative. You know, instead of plus negative, I'll just write minus big G, big M, little m over R initial minus negative big G, big M, little m over R final. Oh, and again, please remember, R final, that's where the radius of the Earth is going to go. Not initial this time. Alrighty. 0.5. What was the mass? 45,000? Fairly big. What was V initial? 5.67 times 10 to the 4th squared minus big G, mass of the Earth, 45,000 all over. Did they give me an altitude or did they give me a radius for my initial location? How do you know it's a radius? Because it says from the... Okay, so 1.2 times 10 to the 7th. I have a minus, which is a plus, ditto mark times ditto mark times ditto mark, all over 6.38 times 10 to the 6th. I think, Thomas, I'm going to do each one of these one at a time to like 5 sig figs and then add them up. I don't think I would try typing this into my calculator all at once. But I do want to encourage all of you to try these on your calculator because you need some calculator practice. For kinetic energy, I get 7.2335 times 10 to the 13th. I need a confirmation before I write that down. 7.2335 times 10 to the 13th. Take away 6.67 scientific notation, negative 11 times 5.98 scientific notation, 24 times 45,000 divided by 1.2 scientific notation 7. No squared here. You get 1.4957 times 10 to the 12th with a minus sign in front of it. 1.4957 times 10 to the 12th, and then plus, I think the second term I can just backspace edit and change the 6.38 times 10 to the 6th to the radius. 2.8133 times 10 to the 12th. So my final kinetic energy is going to be 7.2335 scientific notation button 13. Take away 1.4957 scientific notation button 12 plus haha answer button. See if you get 7.365 times 10 to the 13th. I got some nods. is that big? Tough for me to say because I don't have a context. Well, I do. On the next page, I wrote an atom bomb that exploded over Hiroshima was around 6.3 times 10 to the 13th. So this is slightly larger than a small atomic bomb. Would this do damage? Yeah. How fast would it be traveling at impact? Ooh. Steph, what's this want me to find? Speed. What did I just find? Did I write how much work? I did not find how much work. What did I just find? I found the kinetic energy. Oh, that has speed in it. You know what? I think I would write KE equals a half mv squared. How would I get the v by itself? Times by 2, divide by little m, square root. 2. I still have my answer button, I hope. So, times by 2, answer button, divide by 45,000, square root. You get 57,200? 57 kilometers per second. Would this do damage? Yeah. A lot? Fair bit. So in 2029, there's a football-sized stadium asteroid that's probably due to hit us. So it would do a fair bit of damage. You didn't know about the football stadium-sized asteroid? Really? Put your pencils down and look up. Boy. Kiefer's awake now. Geosynchronous satellites maintain their orbit over the same place on the Earth at all times. In fact, they stay above the equator. I talked a little bit about geosynchronous satellites in our orbits lesson. What would the period be of any satellite? If it appears to stay above the same place on the Earth at all times, so that it's matching the Earth's rotation, what must its period be in hours? It's got to be 24 hours. Which is how many seconds? Times by 60 times by 60. I think it's 84,600 seconds. I didn't, yeah? 86,400 seconds. Yeah, I didn't do that one in my head. And then I think I mentioned to you, if you look at your formula sheet, the formula sheet says the period of the Earth is 86,100 seconds. And I mentioned it depends on what you mean by Earth's rotation. If the Earth is just rotating on its own axis, all the way, that's 86,100 seconds. But if we factor in the sun and the fact that the sun is moving through the, and we are moving around the sun, our 24-hour day, which is measured by the sun, is 86,400 seconds. I don't care which one you use. I typically use the 86,400, which probably for orbital mechanics is technically wrong, but I just know I go 24 times 60 times 60. I won't be fussy. What would the radius of such a satellite be? Ethan, are we in orbit? Then gravity is what's pulling me in a circle. In fact, big G, big M, little m over r squared equals little m 4 pi squared r over t squared. Ooh! This is that cube root one again, isn't it? I'll get an r cubed and then cube root. I think I'll end up with r equaling the cube root of big G, big M, T squared all over 4 pi squared. Let's see if we can go straight to our calculator just to kind of cut corners. On a test, I would definitely show what numbers I was entering. 6.67 times 10 to the negative 11 times 5. You know what? Let's try this in one step, Mr. Dewick. Cube root of 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 86,400. Don't forget the squared. Divided by bracket 4 pi squared. Do you get 422,507,474? You get that? Hey, let's be clever and even do this, Mr. D. So I get 4.23 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. How high is that? Well, if I take this and I subtract the radius of the Earth and then divide by 1,000, it's about 36,000 kilometers up, which means that's a lot of potential energy fuel to get them there. But it's so handy to have a geosynchronous satellite. We'll spend the money. All of our GPS satellites are geosynchronous. Many military satellites are, because that means many communication satellites are, because that means you can point your satellite dish at one location at all times, and you know there's a satellite there. And they're high enough that even in the northern latitudes, they'll be near the horizon, but we can still spot them. I can't remember how high you have to go or how low you have to go along Earth's surface before the curvature of the Earth blocks the communication satellites that we have in a ring around the equator, but they're really handy. Now let's talk about black holes. Example 3. Suppose an 18,000 kilogram spaceship's orbiting a black hole at an orbital radius of 8.8 times 10 to the 9th meters. The black hole has a mass of 6.8 times 10 to the 32. What's the mass of the sun? 10 to the what? I don't care about the number, but what's its 10 to the? And this is 10 to the 32. This is roughly 100 times heavier than the sun, very roughly. The sun actually is too light to form a black hole. I think the cutoff is once you get around 30 times more massive than the sun, then it's possible for a star of that mass to start, perhaps, depending on a bunch of other factors, to form a black hole. Kyle, what's A asking me to find? Well, Kyle, let me ask you this. Is A asking me to find that? How do you know? Because if I wanted you to find that, what word would I use? It begins with F. Force. This is asking me to find gravitational field. Were you the one I picked on last time? And good. Now you'll make sure you get that correct. Then my work here is done. And again, Kyle, the only equation that I've given you for gravitational field is that one, which really comes from Physics 11. I got the obvious one, mg, and I got the g by itself. But now that we're going cosmic, big G, big M, little m, over r squared over m, this gives us our gravitational field strength equation. It's big G, big M over r squared. By the way, just again for purely nerd trivia, once you've written that down, if you look up, this is an acceleration because I got it by going force divided by mass. So if I multiply it by mass, now it's a force. If I multiply it by mass, now it's a force. You can see that's hidden in the gravitation equation as well. Let's crunch the numbers here. So it's going to be big G, 6.8 times 10 to the 32 all over, and that is an orbital radius, so I can use that, and don't forget the squared. It's going to be bigger than 9.8. What do you get? $585, is that rounded off properly? 586, is that rounded off properly? Really, I had to remind you. 586? What would the units be? You could say meters per second squared because it's an acceleration. I typically go with newtons per kilogram because that pops right out of the definition that I gave you so that I don't have to memorize units or even realize, it's an acceleration. But it is an acceleration as well. What's Earth's gravitational field strength? 9.8. 9.7997. If you actually crunch the numbers, close enough to 9.8 that we don't care too much. Is that okay, Kiefer? Would this be fatal to those on board the spaceship? It's about 59 Gs. Would that be fatal? While in orbit, they won't feel it at all because they're in free fall. While arriving or leaving, they'll probably feel it then. So this is purely a hypothetical question because let's assume that if we ever have the technology to explore black holes, we'll have Star Trek teleportation technology. So maybe we would beam them in there directly at speed in orbit, and then they could stay there quite nicely. By the way, the other issue that they would also be affected by there is in that strong a gravitational field, Einstein's general relativity says time would be moving far slower for them, and so they would experience time dilation. So they might be exploring for one of their years and come back out, beam them out, and to find 11 years have gone past back with the rest of us. What's the escape velocity required to leave the black hole's gravity well? Does anybody remember the escape velocity equation? Okay. We can derive it from kinetic energy if we wish, but yeah, escape velocity. So big G, big M over R, that was orbital speed. That's escape velocity. What do you get? You know, if you just backspace, I bet you already have the big G, the big M, and the R already typed. You can probably just delete the squared and times by 2 and then square root that answer. It's going to be big. Caleb, what'd you get? In scientific notation, please. You're way off. There's no way it's 301 meters per second. That would be far less than leaving the Earth at 9.8. I guess I'm going to have to type this. Okay. 3.21 times 10 to the 6th. 3.21. Anybody else? Yep. Meters per second. Is that your first mistake of the year? Oh, okay. Okay. So, let's suppose astronaut Kiefer is on this mission, and he has been assigned to do a spacewalk. But Kiefer, being Kiefer, forgets to clip his spacesuit onto the side of the space station. And suddenly, before he knows it, he sneezes, and in sneezing, he accidentally pushes himself away from the space station. and slowly starts to spiral in and spiral in and spiral in. What would it be like to fall into a black hole? Well, while you were in free fall, you wouldn't notice the increasing gravitational field strength, and you would be in free fall while you were spiraling in, except eventually when you were getting near the event horizon, just the fact that you're fairly tall, let's assume you're going feet first, just the fact that you're fairly tall, G on your feet would be different from G on your head. You would feel a stronger tug on your feet. And initially, it would feel pretty good, kind of like when you stretch in the morning. But then rapidly, it would go from feeling pretty good to medieval torture rack stretching to, oh my goodness, I've never felt it. In fact, as you fell, it would reach the point where the difference on the tug of your feet and the tug of your head would overcome the atomic bonds that hold you together, and you'd probably bifurcate right around your center. And then those two pieces would also split in half as they continued to fall. And those four pieces would also continue to split in half and split in half. And this process would go on over and over. Not only that, because the black hole's gravitational field strength is so strong at this location, it's also warping the very curvature of space-time. You would also be getting squeezed inwards like toothpaste being squeezed through a toothpaste tube. Until eventually you would end up a stream of atomic particles slowly spiraling your way into the black hole. And once you pass the event horizon, as far as we know, you're lost to the universe forever. We have a name for this process. Does anybody know what physicists call this process of being split and crushed while you're falling into a black hole? We call it spaghettification. You don't need to know that word, but that's a word that's worth adding to your vocabulary. Spaghettification. The word spaghetti with a fication on the end. But I also need to point out, once you cross the black hole's event horizon, currently our physics breaks down. So much of this, what goes on inside, is very speculative. But it also means, because clearly the insides of black holes must exist, there are many of them in the universe, it means our current understanding of physics is incomplete. So the two best theories we have for explaining what's going on in the universe are Einstein's theory of general relativity and quantum physics. Those both must be incomplete because they don't explain some key ideas. Your homework is to start working on the ultimate review. But first,